Temperature and the Zeroth law of thermodynamics. In this session, we will explore the fundamental concepts that allow us to define and measure temperature. Our discussion begins with the basic ideas of thermal contact and thermal equilibrium, which lead us to the formal statement of the Zeroth law of thermodynamics. We will also examine how thermometers function by relying on various physical properties that change with temperature. By the end of this outline, you will understand the macroscopic basis for temperature and how we can reliably compare different systems using a quantitative scale. We often begin our understanding of temperature based on our physical senses, categorizing objects qualitatively as either hot or cold. However, human senses are actually unreliable indicators of true temperature. For example, if you step on a tile floor and a carpeted floor that are in the same room, the tile feels significantly colder. This happens because the tile transfers energy away from your skin at a much higher rate than the carpet does. Our skin is essentially measuring the rate of energy transfer rather than the actual temperature of the object. To study physics, we need a more objective and reproducible method for measurement. To understand temperature more formally, we must define thermal contact and thermal equilibrium. Two objects are in thermal contact if they can exchange energy through heat or electromagnetic radiation due to a difference in their temperatures. When these objects are allowed to interact, they will eventually reach a state called thermal equilibrium. In this state, the two objects no longer exchange net energy. Typically, if two objects start at different temperatures and are placed in contact, they will eventually settle at a shared, intermediate temperature. This process of reaching a steady state is the foundation for all thermal measurements. The Zeroth law of thermodynamics is the cornerstone of temperature measurement. It states that if two objects, let us call them A and B, are each separately in thermal equilibrium with a third object, C, then A and B must be in thermal equilibrium with each other. In this scenario, object C acts as a thermometer. This law is Zeroth because it provides a logical foundation that must exist before we can define the first and second laws. It allows us to define temperature as a specific, measurable property that is shared by all objects in thermal equilibrium with one another. We can visualize the Zeroth law using a simple experiment with three objects. In the first two frames of the diagram, we see a thermometer, labeled as object C, being used to measure objects A and B separately. The digital display on the thermometer shows a reading of 22.5 for both. Because object A is in equilibrium with C, and object B is also in equilibrium with C, the Zeroth law tells us that A and B are in equilibrium with each other. As shown in the final frame, if we then place objects A and B in direct thermal contact, no energy will be exchanged between them because they are already at the same temperature. We can now formally define temperature as the physical property that determines whether energy will transfer between objects in thermal contact. If two objects are at the same temperature, they are in thermal equilibrium, and no net energy flows between them. If there is a temperature difference, energy will naturally transfer from the object at a higher temperature to the object at a lower temperature. An important point to remember is that this transfer and the resulting equilibrium depend only on temperature. Other factors, such as the size of the objects, their total mass, or the specific materials they are made of, do not determine the direction of energy flow. Thermometers are tools that allow us to quantify temperature by monitoring physical properties that change in a predictable way. There are many properties we can use. For instance, common thermometers measure the change in volume of a liquid, like mercury or alcohol. We can also measure the changing dimensions of a solid, or the pressure and volume of a gas. In more technical applications, we might look at the electrical resistance of a conductor, or even the change in color of a hot object. To make these observations useful, we must calibrate the device by placing it in contact with a known natural system to establish a standard scale. Let us test our understanding with a quick quiz. Imagine two objects that have different sizes, different masses, and different temperatures. When these two objects are placed in thermal contact, in which direction does the energy travel? The options are from the larger object to the smaller one, from the more massive object to the less massive one, or from the object at a higher temperature to the object at a lower temperature. Based on what we have discussed, the correct answer is C. Energy transfer is driven solely by the temperature difference, regardless of size or mass. To summarize what we have covered, temperature is a macroscopic measure of how hot or cold a system is, and it is formally defined through the Zeroth law of thermodynamics. Thermal equilibrium is the state reached when energy exchange between objects stops. The Zeroth law is vital because it justifies our use of thermometers to compare different systems. Finally, we saw that a wide variety of physical properties, from liquid volume to electrical resistance, can be used to create the quantitative temperature scales we use in science and everyday life. We conclude with two review questions to think about. First, consider why the Zeroth law is considered the essential basis for all temperature measurement. Reflect on how it allows us to use a third object to compare two others. Second, think back to the example of the metal rod and the wooden block. If both are at 20 degrees Celsius, why does the metal rod feel colder when you touch it? Use the concepts of energy transfer rates and the limitations of our senses that we discussed at the beginning of this session to explain this phenomenon.